Hi everyone. Today we begin a very important topic called rules of counting. Whenever we want to know how many possible outcomes, choices, or arrangements exist, we use counting rules. Instead of writing every possibility one by one, these rules help us count quickly and accurately. By the end of this lecture, you will be able to solve many practical problems involving choices, selections, and arrangements. So let's start. First, let's learn what a sample space is, why is it important to list a sample space, and how to list the outcomes in a sample space. So let's first discuss what a sample space is. A sample space is the set of all possible outcomes of an experiment. It is usually represented by symbol S. Now, size of a sample space is the number of outcomes it contains. It is denoted by N of S. N of S means number of sample points in a sample space. For example, let's consider an experiment of flipping a coin. When you flip a coin, so there are two faces of a coin. So you may get head or tail. So the sample space for this experiment is this one. The sample space for this experiment is denoted with capital S, and in curly brackets you put head and tail because these two are the all possible outcomes when you flip a coin. So number of elements or number of sample points in a sample space is 2 because head and tail are only the two options when a coin is tossed once or a single coin tossing experiment. Similarly, when you roll a die, a six-sided die or a six-sided dice, then all possible outcomes of any dice is 6, which contains 1, 2, 3, 4, 5, and 6. But when you list the sample space, so this is from 1 to 6. And the number of sample points or the number of elements in this sample space is 6. So this is how you can list the outcome of any experiment. So in this case, the experiment is simple. Now let's consider more experiments. Suppose for a fair coin toss, each toss has two possible outcomes, that is head or tail. On a single toss, when you toss a coin or when you toss a single coin, so we discussed it here that the sample space is this. So again, the sample space is this. Now the number of sample points in this sample space is 2. Okay, and this is obtained from this 2 to the power 1 because the outcome or possible outcomes of a coin is 2 and we tossed it one time. So this is 2 to the power 1, which is equal to 2. So total outcomes will be 2. On a 2 tosses, when 2 coins are tossed at once, then the sample space will be this. The first may appear head, the second may appear head. The first may have head, the second may have tail. The first may have tail, or the second may have head, and both may have tails. And number of sample points in this sample space is 4 now, because 2 to the power 2 is equal to 4. 2 faces of the coin, and you toss 2 at a time, then the resultant value is 2 cross 2. Similarly, when you toss a coin 3 times at once, then this is the sample space, and again the number of sample points in this sample space is 8, and this is obtained by 2 to the power 3. That is, 2 to the power 3 gives us 8 outcomes. So these are total 8 outcomes: 1, 2, 3, 4, 5, 6, 7 and 8. On 4 tosses we are getting 16 outcomes, and the listing of this sample space will be like this, and this is due to 2 to the power 4. Now when you continue this procedure, so on n tosses you will get all sequences of head and tails of length n, and number of possible sample points, or all sample points in a sample space, will be 2 to the power n. Now listing this is almost complicated or impossible. Now here is a tree diagram. Like, this is the first toss, you are getting head and tail only. In the second toss, this is now head, 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 tail, tail, head, tail, tail. So you can make a sample space out of this. So 4 points. First will be head, head, then head, tail, then tail, head, then tail, tail. You can tally this with the sample spaces listed above. Similarly, in third toss, you will get 3: head, 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 tail, then head, tail, head, head, tail, tail, then tail, head, head, tail, head, tail, and then tail, tail, tail. In 4 tosses, this will be your final sample space, or all possible outcomes. Now if you continue this, then the tree diagram will also be getting complicated. Now we roll a dice here once, and this was the sample space, which is all possible outcomes of the sample points in a sample space. So here we are rolling a 6-sided dice, a choice. Now what happened when we do this? Then the sample space will contain all pairs from here to 6 to 6. That is, we are getting 36 pairs, because we have 6 faces of each die, and when you throw it or roll it twice, then you are getting 36, because 6 cross 6 is equal to 36. Now here we are able to list the sample space of rolling 2 dice, and this is the possible picture or the possible outcomes we can obtain, and this is now further converted into number. But when you throw a dice 3 times, then it is now difficult to list the sample space. Here in this case we were able to do so, but when we increase the number of throws or the number of rolling, then we are getting complicated sample space, and listing is almost impossible. So when the sample space is small, we can list all the outcomes, but when it becomes large, we use rules of counting. Further, we are going to discuss rules of counting. There are 3 main rules you need to know. The AND rule, that is the rule of multiplication. The OR rule, the rule of addition. And the rearranging rules. This rearranging rules using factorials. So let's discuss these rules one by one. We use rule of multiplication when we need to do one thing and another thing. Like if you have A ways to do the first thing and B ways to do the second thing, then you need to multiply. For example, you have 3 shirts and 4 pants. So how many ways you can wear them? So the total number of ways to wearing these 3 shirts and 4 pants is 3 cross 4, which is equal to 12, because for every shirt you can wear all pants. This can be explained like this. The above phenomena can be explained using a tree diagram, that is to check how many possibilities you can obtain. So you have 3 shirts. So first one is S1, shirt 1, then suppose S2, then suppose S3. Now for each shirt you can use P1, then P2, then P3, and then P4. Same goes for S2, and same goes for S3. Then you can connect them. Now connect S1 with P1, S1 with P2, S1 with P3, S1 with P4, S2 with P1, S2 with P2, then P3, S2 with P4, S3 with P1, S3 with P2, and S3 with P3. So the outcomes will become S1, P1, then S1, P2, then S1, P3, and so on The last one will be S3P4. S3P4, and this will be total 12 outcomes. The second one is rule of addition, the OR rule, OR. Okay, now this rule is used when you can do one thing or another thing. You can't do both at once. For example, there is an example of a meal. Suppose you have A ways to do one thing and B ways to do another thing. So you need to add them. Here an example is given. You can choose 3 sandwiches or 4 salads for lunch. So total choices are 3 plus 4, which is 7. That is, if you have 3 sandwiches and 4 salads, then by adding these two you have 7 options, but you need to pick one for the lunch. Suppose this is our lunch, and for our lunch we have sandwiches and salads. Now suppose sandwiches are represented with S1, S2 and S3, whereas salads let's represent with A1, A1, A2, A3 and A4. Now this is total 3 and this is total 4, which makes 7. So you can choose only one of them. We have to choose one meal out of 7. That is, we have to choose either S1 or S2 or sandwich 3 or salad 1 or salad 2 or salad 3 or salad 4. Okay, now in multiplication rule you see that we move through multiple stages. Now the outcomes will be like this. Total outcomes will be here. Like suppose this is S1, P1, then S1, P2, then S1, P3, then S1, P4. Again S2, P1, S2, P2, S2, P3 and S2, P4. Then S3, P1, this is 3, then S3, P2, then S3, P3, then S3, P4. So this gives us total outcomes 12. This is one pair, this is second, third, four. Similarly, 1, 2, 3 and 4, and then 1, 2, 3 and 4. So 4 plus 4 plus 4 gives us 12. 12 outfits. That is, you can wear 3 shirts and 4 pants in 12 different ways. But in addition rule, you have to stop. You don't have to branch out it further. Either you need to take salads, 3 of the salads, or 3 of the sandwiches, or 4 of the salads. So this is the main difference. We are restricted to one branch. This, out of these 7, select one. Okay, the third one is the rearranging rule. This rule is used when you want to know how many ways to arrange things. In simple words, to arrange n different items in a row, you multiply all numbers down to 1. For example, let then this n is equal to 3. Suppose we have 3 books. N is equal to 3. And one book is A, the other book name is B, and the third book name is C. And you are going to arrange this A, B, C books on a shelf. So how many ways are there to arrange it? And these are the possible ways. You can put book A with book B with book C, or you can put book A first, then C, then book B, or you can put book B first, then A, and then book C, or you can keep, or you can arrange book B first, then C, then A, and the last one is book C, then book B, and then book A. Okay, here we have 3 different books, A, B, and C. Now we have to arrange them on a shelf. Now the count choices for each position. So first position, meaning that in the first place we have 3 choices, A, B, or C. Second position, we will be having 2 choices after one book is used. And in the third position, 1 choice left only. So first position, then second position, and the third position. And these all will give us 6, or 3 factorial is equal to 3 factorial is equal to 6. Okay, so the 6 arrangements are ABC, ACB, BAC, BCA, CAB, and CBA. Now you have to note that ABC and ACB are different, because in arrangements the order of the book is different. Rearranging rules. We arranged all the 3 books in this example. But what if we don't pick all books, or we pick some of it? So when we put some of it, then 2 situation arises. Whether you are ordering them, or whether you don't order you don't want to order it. If you want to order it, then use permutation. And if you don't want to order it, then use combination. So permutation, pick R items from N and pay attention to the order. Whereas combination, pick R items from N and ignore the order. Now let's take the above example. Let's suppose, or let's consider the three books A, B and C again. Suppose we have three books A, B and C, and let's apply the pick rules. So here there are three books, so we can say that N is equal to 3. Now we want to choose two books from it. So let's choose two books out of it. Now let's arrange two books at a time. So if you want to consider the order, then you need to use permutation. Like if you want to consider the order, then for order you need to use permutation. And permutation formula is N P R, which is equal to n factorial divided by n minus r factorial. When you put these values in this formula, so 3PR is equal to 3 factorial divided by 3 minus 2 factorial. So the resultant value will be 3 factorial, because 3 minus 2 gives us 1 and 1 factorial is 1. So how to open this 3 factorial? Here is the opening formula. Multiply all numbers down to 1. So all numbers down to 1. So down to 1 we are getting 3, 2 and 1. So total are 6 possible ways to arrange two books out of 3 when order matters. So how you will form this order? So this order will be, okay, so the total arrangements are 6. Now let's see what are they. So 3 books, and keeping two books at a time, we can arrange it in this way. Now book A may be placed with book B, book A with C, book B with A, and book B can be put with book C. Similarly, C with A and then C with B. C with book A and C with book B. So these are the all possible arrangement, which is 6. like this. And this is like this. Okay, now you can also plot it on a tree diagram, or you can represent it with tree diagram. So 3 books you have, A, B and C, and B with and C can be kept with A, sorry, B and C. Repetition is not allowed, but order matters. So B, A and C will goes with B, and for C, A and B can be put. So the first arrangement is AB, then AC, then BA, then BC, then CA, and then CB. So these are the 6 possible ways to arrange 2 books at a time out of 3. Okay, so this was about permutation. Now let's use combination when order doesn't matter. So if you have 3 books, A, B and C, that is n is equal to 3, and you want to pick 2 out of it, and if order doesn't matter and or you don't want to account order, that is no order. So without order you can use combination formula, and the formula will be n combination r, which is equal to n factorial divided by r factorial into n minus r factorial. And when you solve it, that is when you put values in it and C2, so the answer will be 3. Okay, now how you will make this 3, and that will be A will go with B, A will go with B, then the second pair will be A will go with C, and then the last option left, B will go with C. So only 3 arrangements is possible when you don't consider order. Here 6 options are possible of arranging 2 books in a shelf when there are 3 books. So this is the main difference between combination and permutation. Now when to use? So here is a note. Suppose I'm doing task A and task B. So when this is the situation, then use multiplication. Am I doing task A or task B? When there is or you have to do either of it, so you use rule of addition. Okay. The third case is if you are picking items from a group. So does order matters? Then use permutation. If order doesn't matter, then use combination. So here's the conclusion, that this counting rules tells us how many different ways can something happen. Without having to draw a billion stick figures, you just multiply, add or rearrange. Okay, now the question is why we need rules of counting. So we need rules of counting, that is multiplication, permutation or combination, for one fundamental reason, that is to count possibilities efficiently and accurately without listing them one by one. Like suppose here we have some explanations. Okay, but here we have considered an example. Suppose we have to imagine a password of 8 letters, and letters are from A to Z. So from A to Z we have 26 letters. That is, starting from A to Z we have 26 options, and we are going to make a password of 8 letters, and this will be from these 26 options. So how many possibilities are there? So there are 26 to the power 8 possibilities, meaning you multiply 26 with 26 with 26, that is multiply 26 8 times. When you multiply 26 8 times, then you will get approximately 208 billion options. So listing these 208 billions options is almost impossible. So you need a powerful computer to solve this, or to make these arrangements for you, or to forming these passwords of 8 letters. Okay, so this is one way we can avoid using these rules of counting. We can avoid listing all possibilities. So this just gives us all possible outcomes, and we don't need to list the possibilities. Rules of multiplication, we can avoid double counting or undercounting. Like without rules, we can arrange A, B, C and C, B, A, or we might list A, B, C and C, B, A as two different things when order doesn't matter. So this is overcounting. So combination rule automatically correct order. Now the third advantage is it is used for the foundation for probability. So the probability concept is based on this rule of multiplication. Probability is defined as probability of any event is equal to favorable divided by total. That is, probability of any event A is equal to favorable, suppose favorable is M, and divided by N. Now this favorable is the numerator, and you need counting rules to find this favorable. Similarly, to find the total outcomes, you need again counting rules, because this is the total possibilities. Now, if you use counting rules and if you don't use counting rules, then what happens? If you don't want to use counting rules, then you have to list all the possibilities, which is quite complicated. But with counting rules, you can easily obtain all possible outcomes, and there is no need to list them. Okay, now without counting rules, this can, or you can solve tiny sets only, but with counting rules you can works for too many things. Okay, now counting rules is prone to errors, while without counting rules you can create errors or you can do mistakes, but with counting rules there is built-in correction for order or repetition. So without counting rules it's difficult to find probabilities, but counting rules is the essential tool for probability. So in real world applications where counting is required, so one is cryptography. So cryptography, we can assess how many passwords must a hacker try. So how many passwords must a hacker try? You can use n to the power r formula, n to the power r. Similarly, scheduling or scheduling. How many ways to assign 5 shifts to 10 employees? So for this, you can use permutation, that is 10 P5 or NPR. Quality control, so you can use it in quality control, like if the situation is how many ways to pick 3 defective items from a batch, then you can use combination formula, which is NCR. Okay, at the end, here is an exercise for you. The first 3 questions are about multiplication rule. The second 3 questions are about rule of permutation. And the last 3 questions are about combinations. So you can practice them. Here is mixed problems. So you need to identify the rule, that is whether it is from rule of multiplication or rule of permutation or rule of combination. And here is answer key for you. So I hope you have understood today's lecture. Thank you for your attention and look forward to seeing you in the next lecture. Until then, keep practicing and keep learning. Thank you and goodbye.